So next I want to talk about an application of parallel transport. So if you didn't watch the parallel transport video and you don't know what I'm talking about, go back and watch that first. But the application is what's known as holonomy. And the setting is, let's say we have a triangle. On any space, plane, sphere, hyperbolic space. The question is, what happens when you parallel transport a vector all the way around the triangle? What's the new vector you get? Okay, so the picture is I have some triangle like that, and I have a vector on it, call it R, and I want to parallel transport it all the way around the triangle. We're always going to go counterclockwise, just so that we have just so that we're all having the same conventions, so that our answers are the same. If I parallel transport around this triangle, what I mean is I first transport along the geodesic L, which means I keep this angle the same, and I move it down and to the right. So if I extend this geodesic a little bit, move this vector r down until I get some r prime. And remember, parallel transport means that this angle is the same. And then I take r prime and I move it, I transport it along the next geodesic L prime. And so in that case, the angle I care about is the angle with respect to L prime. So I'm taking this vector r prime and I'm transporting it along the geodesic L prime now until I get some new vector r double prime. And I'm keeping the angle with respect to L prime constant as I move r prime to r double prime. And then finally, I go along the third side. Maybe I'll call this one this geodesic L double prime. And if I'm moving along the third side, the angle I want to keep constant is this one. Call it sigma maybe. So I transport r double prime along the geodesic L double prime, and finally I end up with, I move it all the way along, and I end up back where I started with some new vector. And the question is, so okay, what's this new vector? Let's give it a name. I guess I'll call it r triple prime. The question is, what's the relation between the new vector r triple prime and the one I started with, r? And some of you might have a guess from this picture that they should really be the same. I mean, what have I done? I've translated r down and to the left, and then across to the right, and then up and to the left. And those three translations should take it right back to where it started. It should be the same vector maybe. And that's true if you're on the plane. But weird things happen more generally. So if I'm on the plane, so if delta was a triangle on the plane, then this new vector I get, r triple prime, will be the same as the one I started with. But more generally, for instance on a sphere, they may be different. And you can check that pretty easily by looking at a particular example on a sphere. So let's look at our favorite triangle on a sphere, which is the 90, 90, 90, and see what happens. So I want to parallel transport along the sphere. So I start with a little line segment on the sphere, little geodesic segment. I'm going to have it pointing in the same direction as the first geodesic, just to keep my life simpler. And I parallel transport it along L, right? So what I end up with is the same longitude line as L, now here, right? So that was R, here's R prime. And then I parallel transport this one along L prime, so I keep the angle of this vector with respect to L prime constant, which means 90 degrees with respect to the equator. And what I get is another longitude line, still 90 degrees with respect to the equator. Call it R double prime. And then finally, I move R double prime up along L double prime, keeping the angle with respect to L double prime constant. In this case, the angle is 180 degrees. And so I end up with a vector pointing down along L double prime. And that's my R triple prime. Notice that you can clearly see it's not the same as R. They differ by 90 degrees. Okay, and so in general, one can ask, what's the angle of their difference? How much do they differ by? So what's the angle between R and R prime? And that's called the holonomy. Oops. Between R and R triple prime. So this is what you should remember in your head, and then if you're actually doing a calculation, we have to be really careful just to make sure we all have the same conventions. So here's the official definition of holonomy. Given a triangle delta and a vector r on delta, we might as well start at a vertex just to keep things simple. So the vector r has its base at one of the vertices of the triangle. Then what I want to do is do parallel transport along each of the three geodesics, right? And I'm always going to go counterclockwise. If you go clockwise, it might potentially change the answer. Until you return to your starting point. Let's call this new vector, let's give it a name. I'm just going to call it R prime. So it's the one which I was previously calling R triple prime here. But I don't care about the other ones, so I'll just call it R prime now. And okay, so then the holonomy of delta. So it's a invariant of the triangle. So the holonomy of delta is the size of the angle between R and R prime. Between the original and the transported vector. So a couple conventions again, just to make sure we all get the same answers. If R prime is counterclockwise, sorry, I should have added the size of the smallest angle between r and r prime. So there's always two different angles you can form between two rays, and we choose the small one. And then if r prime is counterclockwise from r with respect to this angle, then we make it positive. We have a plus sign in front of the angle. And vice versa. So if the smallest angle between r and r prime has r prime clockwise from r, then we make it negative. Okay, so just as an example, let's say here's one of the vertices of our triangle. Here's our starting ray, r, and we parallel transport it along the triangle, and what we end up with is r prime. Then there's two angles between these. There's this one and that one. We're always choosing the smallest one, so we call that alpha. And in this case, notice that r prime is counterclockwise from r if I move along alpha. So then, in this case, the holonomy is alpha. Okay. In the other case, maybe this is r and this is r prime. Again, I always choose the smallest angle, so that angle is beta. But this time r prime is clockwise from r, so the holonomy is going to have a minus sign in front of it. So in this case, it's minus beta. Okay. Now, the homework question that I want you to do is, given a triangle, and again, it's more interesting if we're not on the plane, but we can be on the sphere or hyperbolic space for this calculation. So given delta, a triangle, with interior angles beta 1, beta 2, beta 3, the question is just calculate the holonomy. And you can kind of guess from the way I'm phrasing this question, the answer should only depend on these interior angles. So you're going to get some formula for the difference between your original vector and your new vector, which depends on those beta 1, beta 2, beta 3. And I'm going to draw this triangle maybe to sort of emphasize that it's more interesting on the sphere. So I'll draw these geodesics a little curved. So maybe that's delta. And I have these interior angles. So I just want you to calculate the holonomy. And a hint is, it's going to be useful to keep in mind, I forget the name of these, but some of the other angles formed by these geodesics intersecting. So I'm going to name alpha I to be pi minus beta I. So let alpha 1 equal pi minus beta 1, and similarly for the others. it's going to be useful or helpful. So that's just a little hint. So the question is to calculate the holonomy. Again, you start with some geodesic R. And my second hint to you is to keep your lives a little bit simpler in terms of just doing this computation. Choose R so that it's lying along the first geodesic. Okay, so you're going to parallel transport along this geodesic, then this one, until you get some R prime. And I want you to calculate the angle between R and R prime. I think that's about all I want to say about it. I guess one final hint is, again, do the sanity checks that you can. So check your final answer with one where you know the answer, which is the 90-90-90 triangle. So in that case, remember, we drew the picture. I move it all the way across. The new vector I get is 90 degrees counterclockwise from R, and so in this case the holonomy should be 90 degrees, or in terms of radians it should be pi over 2. And a second sanity check is check on the plane, where in that case beta 1 plus beta 2 plus beta 3 we know equals 180 degrees, or pi. Then in that case we should get a holonomy of 0. Why is that? Well, because on the plane, as we kind of guessed, actually these two vectors should be equal, because we're just translating around. We end up doing nothing after doing the 3 translations. So that's another homework question. Email me if you have any questions about the calculation. And that's it.